Hello, and welcome to today's ACM Learning webinar. This webcast reflects ACM's deep commitment to lifelong learning, aiming to empower computing professionals and students who join ACM's worldwide community of 100,000 plus members. My name is Yolanda Gil. I am Director of Knowledge Technologies at the Information Sciences Institute of the University of Southern California, and a research professor in the Department of Computer Science at USC, and I will be your moderator for today's webinar. I am a member of ACM, and I was recently re-elected chair of SIGART, the ACM Special Interest Group, which are called SIGs. SIGART is the Special Interest Group in Artificial Intelligence. There's many others. ACM is an incredible organization that supports computing researchers and practitioners through a wide range of programs. ACM maintains the ACM Digital Library, which is the world's most comprehensive database of computing literature. ACM supports many conferences through its special interest groups, very likely ones that you regularly attend. For example, ACM SIGART supports many conferences financially, particularly through student scholarships. ACM also supports the international computing community, linking to professional societies around the world and organizing events of broad interest, such as the Turing Centenary Celebration held last year. When you become a member of ACM, you receive a subscription to the communications of the ACM. This is a fantastic resource to keep up with computing news. And finally, ACM also supports education, including curriculum development, teacher training, and other activities such as this webinar. Let me go over a few housekeeping items before we get started, and you can see them in the slide in front of you. The session is being recorded and will be archived, and you will receive an automatic email notification when it is available. You can share it with your friends. The slides will advance automatically throughout the event. You can enlarge the slides by dragging the corner of the slide window, the lower bottom corner. You can use the widgets that are at the bottom panel of the screen. There's a resource list where you can get a copy of the slides if you would like. At the end of the presentation, we will have time for questions. And if you think of a question during the presentation, please use the Q&A widget at the bottom. You don't need to wait for the end of the presentation to submit questions. And at the very end, after the question-answer period, you'll see a survey URL. And if you fill it out, you will help us improve this webinar experience. And also, you can suggest topics and speakers for future webinars. I'm showing now in your screen the Twitter handle that we're using. The hashtag is ACM Webinar NEL. And you can share this with your friends, and you can also use Facebook to broadcast this. We'll be watching your tweets as we go. Let me introduce today's presentation, which is Never-Ending Learning to Read the Web by Tom Mitchell. Tom Mitchell founded and chairs the Machine Learning Department at Carnegie Mellon University, where he is the E. Fredkin University Professor. He is a member of the U.S. National Academy of Engineering, a fellow of the American Association for the Advancement of Science, and a fellow of the Association for the Advancement of Artificial Intelligence. Tom was on my thesis committee at Carnegie Mellon, and talking to him influenced me tremendously, but his papers also. I remember an unpublished tech report that really cleared up for me a lot of questions about learning bias. It was wonderful, and it was not even published. If you have never read his papers or heard him speak, I'll tell you, you are in for a real treat today. Tom has worked on many aspects of machine learning. He believes the field of machine learning will be the fastest growing branch of computer science during the 21st century, something that I think will be apparent to us at the end of his talk today. His current research uses brain imaging to show how the human brain understands what it reads, And he is also using machine learning to develop computers that are learning to read the web. And this is the topic of today's presentation. Tom, thank you for joining us, and please go ahead.
Okay, well, thank you, Yolanda, and also thank you, ACM, for making it possible for setting up this talk. I really appreciate that. So today I would like to speak with you all about a long-term research project that involves both machine learning and natural language understanding. And you see here some of the people involved in this project. It truly is a group effort. And I'll tell you that this project is really based on two underlying assumptions or tenets. And the first one has to do with machine learning as a field. I think that everybody who's familiar with the field would agree that over the past decade, machine learning has been tremendously successful. We now have, for example, spam filters, which are trained using machine learning to distinguish between emails that are spam or not. We similarly have trained programs to distinguish which credit card transactions are likely to be fraud or not. And both of these are in routine use, and they're just a couple examples. But if you really look at the successes in machine learning, then like the two that I just mentioned, they have this kind of narrowness. Both the spam filter and the credit card transaction classifier are really learning very narrow specific functions that are useful. But if you think about the kind of learning that you and I do, or that your children do, it's much more diverse, right? You learn to crawl, then you learn to walk, you learn to run, you learn to ride a bicycle. In parallel with that, you learn to count, you learn to add, you learn to multiply, maybe you learn algebra, maybe you learn calculus. But, and you learn these in a cumulative way, many different things over years. And you learn them in a particular sequence. It wouldn't make sense to start with algebra and later work on counting. So tenet number one is really that we'll never really understand machine or human learning until we can build machines that, like us, learn many different things over years and become better learners over time. So that's tenet number one. Tenet number two is about natural language understanding. We have many successful natural language processing programs around, like search engines, but those natural language processing systems don't really understand the language. They can search for your keyword in a document, but they can't answer questions about the content of the document. And tenet number two is that if we really want to build natural language understanding systems instead of natural language manipulation systems, any system that's going to understand language has to have its own belief system. And so I would suggest that we'll know that we have a system that understands language if we can give it arbitrary text and it reacts by saying one of these three things here on the screen. Right? If we tell it, let's say, Bill Gates founded Microsoft, then it should say, I understand and I already knew that, or maybe I understand and I didn't know that, but I accept it. If we say to it, Yolanda Gill founded Microsoft, then we might expect it to say, I understand, but I disagree because I thought that was Bill Gates and Paul Allen. So the whole idea of language understanding, really I think we can only talk coherently about that if we have it in the context of a computer program with a large belief system. So today's talk is about our never-ending language learner. We call it NEL for short, which is an attempt to build a system that will learn to read the web and will, as a byproduct, build up a huge belief system about the world through what it reads on the web. So the inputs to NEL are an initial ontology that we use to specify what we want it to read about. We give it categories and relations. We might tell it, well, we want you to read about categories like people, universities, foods, beverages, emotions, And for each of those that we give, we also give a dozen training examples. If we say we're interested in universities, then we say, well, Carnegie Mellon is a university, Harvard is a university, Cambridge University is a university. We give a dozen examples. We also, for relations, for example, a relation like who person founded company. We give examples of Bill Gates founded Microsoft. We also give the web. In fact, Google has generously provided now access to 100,000 search queries to the Google Search API each day, and we use that. And occasional interaction with human trainers, which I hope by the end of this talk will become you, or you will become. Then, given that input, the task for Nell is simple to state. It's got to run forever, and then each day do these two things. Number one, read some more facts from the web and extract those to populate that ontology, that is, to fill in instances of universities and people and relations like who founded which company. And number two, just as important, is to learn to do number one better each day. Learn to read better each day. So how would you know if that was happening? Well, for example, if Nell went back to the same text today that it looked at yesterday, if it had learned to read better, then the evidence would be that it should extract more beliefs more accurately today. So there's the task, and that's easy to say. What is the state of Nell? Well, Nell is now 3 years old. It's been running since 2010. It currently has a knowledge base with about 50 million candidate beliefs. I'll show you some of those in a sec. It's growing. It's learning to read better. In fact, it's a better reader now than it was in May, and it was better then than it was the previous May. It's also learning to reason or draw inferences about the world from the things that it's reading. And it's also now extending that ontology that we initially gave manually. So let's take a look. When I say that Nell has 50 million candidate beliefs, here's a small snippet. Each of these red arrows you could think of as one belief triple. So for example, in the middle of the screen here, you might see the belief that the Maple Leafs play hockey, and that hockey uses the equipment helmet, and so does football. So this is a snippet of the 50 million beliefs that Nell had when I made up this slide. And I should warn you that when I made up this slide, I left out some other beliefs that Nell has which are incorrect. And in fact, if you browse Nell's knowledge base, you'll see plenty of errors in its beliefs. And in fact, although it's not shown on this slide, each of the beliefs that it does have, it has associated with that a confidence, a kind of probability that it assigns to that belief. So that's what Nell's knowledge base looks like. And I want to primarily spend our time here talking with you about what I think are the 4 key ideas that make Nell work to the degree that it does work. But first I want to start by browsing Nell's knowledge base a little bit. So I'm going to switch over, I hope, to a screen share so that you can see me browse Nell's knowledge base. I'll give you a URL at the end of the talk so you can do this too. But what are we looking at here? Well, one thing that Nell does in its attempt to understand the web is whenever it finds a noun phrase, any noun phrase, that occurs multiple times on the web, like in this case the noun phrase diabetes, it tries to classify that noun phrase into one of or more of the hundreds of categories that are in its ontology. And so here we're looking at what Nell believes about the noun phrase diabetes. And one thing it believes, as you can see here, is that it believes diabetes is a physiological condition, that the noun phrase diabetes refers to a physiological condition. And why does Nell believe that? Well, it believes it because it found that noun phrase in the context of various other text fragments, like doctor was diagnosed with diabetes, or preventable illnesses such as diabetes, or related diseases such as diabetes. So you get the idea. In fact, it found the noun phrase diabetes across hundreds of millions of web pages in each one of the contexts that's shown here. And now you get to see a key idea about how Nell is reading. It's not like you and I where we understand every detail of every sentence. Instead, Nell looks across hundreds of millions of web pages simultaneously. It does a shallow analysis of the occurrences of the noun phrase diabetes, and then using all of that accumulated evidence from many different sources, it decides, in this case, that it has overwhelming evidence that the noun phrase diabetes must refer to a physiological condition. Now, the other thing that's interesting about this is, where did Nell get these particular phrase contexts? Well, that's what it's been learning over the last 3 years. We, in fact, did not give it any of these contexts that you're looking at here. It's part of its learning to read means for each of the categories and each of the relations, it has to learn these different contexts. So let's just kind of scroll around and see what else Nell believes about diabetes. It also believes it's a disease. And again, you can see a variety of phrases that it uses to determine that a noun phrase is a disease. What else? Well, there's some relations that it believes that diabetes is involved in. One of them, which I consider kind of silly, is it believes there are certain years in which diabetes exists. I would call this a mistake or a silliness on the part of Nell, but it doesn't yet understand time very well. But it has evidence that diabetes occurred in February 1999, for example, in this phrase, and similarly for some other years. That's not too interesting, but it shows you the kind of non-human beliefs that Nell can develop. It also believes that certain animals can develop diabetes. It believes cats can, dogs can, mice can, rats can, children can, kids can, and other things. And again, for each of these, the reason it believes that dogs can develop diabetes is that it finds phrases like dogs that suffer from diabetes, for example. Okay, what else? Well, Nell believes there are certain emotions associated with diabetes. Distress, numbness. It believes certain foods can cause diabetes. Sugar. What else? Oops. Carbohydrates, carbs, glucose. So it has a number of types of relations that it believes diabetes can be involved in. It believes certain foods can decrease the risk of diabetes. Coffee, grains, whole grains, and that certain drugs can treat diabetes, Avandia and so forth. And of course, each of these entities that we look at, like whole grains, are themselves noun phrases that Nell has separately read about and developed some beliefs about. So whole grains, it believes, are an agricultural product of food and possibly a fruit, and that whole grains include a variety of more specific items like barley and oats and so forth. So you get the idea. What I wanted to do here was primarily just show you what that knowledge base looks like and show you some of the reasons why Nell develops these beliefs. So if we now turn back from browsing the knowledge base to instead look at, well, how does Nell really work? Then I'd like to use the rest of our time that way. So Nell is a pretty complex system, but in fact, I think there are 4 good ideas in there. And Nell is in need of many more good ideas, but I want to at least tell you about these 4, and we can point out some of the shortcomings as we go as well. The first idea, which I think is really the key one, this is the one that got the project off the ground. We spent a couple years just kind of spinning our wheels before we succeeded in letting Nell run for more than a week without crashing. Or not crashing in the literal sense, but just doing stuff that was so poor that we stopped it ourselves. the very first question you have to ask is how is Nell learning those kind of phrases that we were just looking at that allow it to determine which noun phrases fit into which categories, or which pairs of noun phrases satisfy which relations. And so let's look at that. Remember that the training data it has available is mostly the unlabeled web. It has a little bit of labeled data. Remember when I said the inputs to the system include the ontology, and for each category we put in the ontology, or each relation, we give a dozen examples. So on this slide, let's look at the problem of learning to determine which noun phrases refer to cities. And suppose I give you these 4 training examples of cities. Then you might think of the following algorithm. You might think, well, let's look at the web. We'll look up these 4 noun phrases, Paris, Pittsburgh, etc., and let's start by finding contexts in which those occur. And we might find mayor of Paris, mayor of Pittsburgh, live in Seattle, so forth. And then we'll use those contexts to find other noun phrases that fill in the ARG1 slot. And we might find mayor of San Francisco, live in Berlin. Unfortunately, we'll also find live in denial. That's out there on the web. And so now we might say, okay, our algorithm will use these 3 new noun phrases as though they're cities as well. Now we have 7. We can look for even more of the surrounding context. And we might find San Francisco is home of, and denial, and traits such as denial, and so forth. So if we iterate this semi-supervised learning algorithm, semi-supervised in the sense that we have just a little bit of supervised training data, the 4 initial ones, and the rest is unlabeled data, then it's a pretty good idea for the first few iterations. But if you let it run for 3 years, it's not really very effective. And the problem is actually not with the algorithm. Or let me just put it this way. I don't think one can find a better algorithm if you insist on framing the question this way. So I think the problem here is that we've misformulated the question. We've made an under-constrained problem. If you think about it, if the only thing I tell you about my secret category that you're supposed to learn about is that here are 4 members of the category, Paris, Pittsburgh, Seattle, Montpelier, you don't know, maybe I have in mind North American cities, or North American cities with at least 3 letters that begin with a consonant, or the union of character traits in cities. So it's hard to blame the program for coming up with the answer that it did, given the way we framed the problem. And so this leads to key idea number 1 out of the 4 in Nell. Key idea number 1 is don't even try to solve that particular learning problem. It turns out to be too hard, too underspecified to get a computer program to learn a category in isolation from a very small set of data. It turns out to be much easier, and this is what makes Nell work as well as it does, to force the system to simultaneously learn many, many different functions in a way that they're coupled and that it must maintain some consistency constraints among them. So let me show you what I mean by that. So here, let's consider, again, learning just a single function that's classifying noun phrases. That's what the NP stands for here, noun phrase. And function F1, represented by that black arrow, we're going to learn that function by training some weights on that function that will look at a noun phrase represented by the phrases that occur around. So suppose, let's take the noun phrase bystricky, a noun phrase you probably haven't heard before. But we could look up on the web and we could see how often bystricky occurs with these different phrases. Bystricky is a friend, rang the bystricky walked in. And function F1 could learn based on those frequencies to classify an arbitrary noun phrase according to whether it's a person or not, based on those phrase frequencies. And off on the right, what you see is the standard machine learning supervised training objective. That is, when we learn the weights, when we learn the F1 function weights that go with each of those clues about bistricky, like how frequently it occurs with is a friend, we choose the weights of F1 so that they minimize the difference between the prediction of F1 for an arbitrary labeled noun phrase and person, which is the actual label. So in other words, in English, this objective is to pick the weights on the features of the noun phrase to minimize the number of mistakes it makes on the labeled training examples that were given. But now here's the key. Suppose instead of learning one function, we learn two. Suppose that in addition to the red function, we learn, oh my, okay, this looks a little upside down. You may have to stand on your head for this one. Suppose we learn the second function, which the blue one here is totally ignoring the phrases, the context around bistricky. Instead, it's looking at the character string bistricky, and it's using features like, does that character string, is it capitalized? Does it end with the three letters SKI, and so forth? And we could similarly train function F2. In this case, though, the important point, and this is at the heart of it, is now what is the objective that we're going to optimize when we train our system? Well, like before, we have the first term in our objective is to minimize the number of mistakes F1 makes on the label data. And the second term requires that we minimize the number of mistakes F2 makes on the label data. But the third term, this is the key one, shows that, in fact, for every unlabeled noun phrase, like O'Hara and table and beverage, even though we may not know a label for that, maybe nobody told Nell the label for those noun phrases, the third term in this objective requires that F1 and F2 agree on the label, even if it's unknown. That is, we want F1 and F2 to eventually, if they're right, they're both going to agree on whether or not this unlabeled noun phrase is a person or not. And so the third term in this objective is the key. It says that for every unlabeled noun phrase we can find, there's a kind of consistency constraint that F1 and F2 must agree. And so every unlabeled noun phrase we find out there on the web, and trust me, there are hundreds of millions of them, becomes a valuable constraint on the joint training of F1 and F2. So that's the key. Key idea number one is to couple the training of multiple functions with some consistency constraints among them. So that's what happens with Nell. And in fact, there are several different ways that functions get coupled. One is that, in fact, Nell does use those different views of the noun phrase to try to predict the same label with different learned functions. But it also is simultaneously learning these black arrow functions that predict different labels. Not only is Nell trying to learn which noun phrases refer to people, but also which ones refer to sports. And it knows that you cannot simultaneously be a sport and a person. And also is trying to learn which noun phrases refer to athletes, and it knows that to be an athlete, you must be a person. So again, there are these coupling constraints that, even with unlabeled data, allow these functions to interconstrain one another. Finally, there's a third type of coupling that has to do with the relations that Nell is learning. And so, for example, remember, Nell is not just learning to classify individual noun phrases, but it's also learning relations, like, for example, which athlete plays which sport. And when we define that relation in the ontology, we type the arguments of the relation. We tell Nell, we want you to learn athlete, play, sport relation. And by the way, the first argument has to be an athlete. The second argument has to be a sport. And so that gives a third type of coupling. That is, namely, that in order for two noun phrases to satisfy the relation, that the first one plays the second one. The first one has to be an athlete, the second one has to be a sport. And so these three classifiers, these three black arrow functions must also agree. So when you add this all up, in NEL, there are thousands of these separately learned functions that are being trained, but they're being trained using that little bit of labeled data and a ton of unlabeled data. And the unlabeled data becomes more and more valuable for training the more densely interconnected this network of different black arrow functions is, interconnected by those different kind of consistency constraints. So that's really key idea number one in NEL. And if that's the only thing you get out of NEL, out of this talk, that's probably the single most important idea that got us from wanting to build a system like NEL to actually experimenting with one. So then what are the things that NEL learns? Well, it learns these kind of extraction patterns. These are very similar to the ones we were browsing when we were looking at diabetes. But what about that second kind of function that's looking at the character string of the noun phrase? What do those things look like? Well, here you see, for example, the top three lines indicate part of what NEL has learned about to decide which noun phrases refer to mountains. It has learned in the first line that if you have a noun phrase like Pikes Peak, where the last word is peak, then there's a high positive weight, plus 1.7, suggesting that noun phrase probably does refer to a mountain. And similarly, in the second line, if the last word is mountain, that's a positive indicator. However, the third line tells that if the first word is mountain, like mountain bike, then there's a negative weight. Probably that's really not a noun phrase that refers to a mountain. So that's the kind of thing that NEL is learning. And you see, these are the two of the views that NEL is using for learning how to read, and those co-train one another, and since they tend to make independent errors, tends to help to have them train each other. Okay, so this leads to a very simple software architecture for NEL, which is effectively that there is a knowledge base shown in red here, the red block. That's what we were browsing. That's NEL's set of beliefs. And NEL is in an infinite loop. On each iteration through the loop, it does two things in a way that's pretty much an expectation maximization algorithm in machine learning terms, or an EM algorithm. Each time through the loop, it does the following two steps. First, each of those different types of readers, like the one that's learning the context patterns for extraction, the one that's learning the morphology clues, looking at the character strings, and a third one that I won't go into the detail of, which is learning web page specific wrapper functions. Each of the learners gets to retrain itself using the current knowledge base as its set of training data. Then to complete the loop, each of those retrained readers then gets to go back and reread the web, or some fraction of it that they choose to, and propose more candidate beliefs, which are then integrated by the evidence integrator to make the final decision about how to update the knowledge base. So NEL is in this infinite loop of update the knowledge base with your current readers, use the knowledge base to retrain the readers. And if you have additional ideas for algorithms that should go alongside in parallel with the ones shown in the green box here, then it's easy to simply add those to the architecture. Okay, so that is really what I have to say about key idea number one. Key idea number one, again, to say it in a sentence, is if you're trying to learn from mostly unlabeled data, then couple the training of thousands of functions and you'll find you're more successful. This leads to an obvious question, which is if coupled learning is the key, then how do we get new coupling constraints? And key idea number two in NEL is you learn them. So think about it. Now that Nell has a knowledge base of 50 million candidate beliefs, some of which are wrong, but on the whole they're more correct than incorrect, it can data mine that collection of beliefs, and it does. It data mines it to learn rules like the one shown here inside the red box. In English, that red box rule states the following. With probability 0.93, you should infer that athlete X plays sport Y if you know that athlete X plays for the team Z and team Z plays sport Y. If I play on the Yankees and you know that the Yankees play baseball, you should infer that I probably play baseball. Now that's common sense for you and I, but it wasn't for Nell until it learned this rule. And again, this is not a rule that it read from text on the web. Nobody wrote down that rule, or at least Nell never found one. Instead, this is an empirical regularity that happens to hold among the thousands of people Nell has read about and the hundreds of sports and relations that it has extracted about who plays on which team and which sports those teams play. It's just an empirical regularity. And so key idea number 2 in Nell is once you've reached the stage where you have a large, even not perfectly correct knowledge base, you can data mine it to learn regularities that hold in the world you're reading about. And then this, in fact, at this stage, Nell has thousands of these kinds of rules. Here are a couple other. The first one says, for example, you can infer that athlete X plays basketball if you know that athlete X plays in the league NBA. So many of these rules are common sense type rules. Nell uses these in 2 ways. They have 2 influences on Nell. First, it uses these rules to infer new facts to add to the knowledge base, even if it hasn't yet read them. And second, they feed back indirectly to improve its ability to learn to read even better. And to see how that works, think about this rule again, which used to be in a red box, now it's in a blue box, and think about that collection of coupled functions that we were talking about a moment ago. Well, this new rule is really a new coupling constraint, a probabilistic coupling constraint that essentially constrains for 3 noun phrases that we're looking at, what are the legal labelings for these 3 relations, play sport, plays for team, and team play sport. And those relations are coupled now by this new constraint, which is the blue rule. And so here we have an example of this virtuous cycle. So think about what we just saw. Nell started out learning to classify noun phrases and into categories, and to classify pairs of noun phrases into relations. But after it built up a big enough knowledge base, then it was actually in a position to learn these rules, like the one we're looking at here. And by virtue of learning those rules, it can now do an even better job of the semi-supervised learning of those reading strategies, simply because these rules it's learning become useful constraints for even more tightly coupling the training of those reading functions. And that's the key, I think, one of the keys to never-ending learning. If you want to build a system that learns well over years, you're going to have a way that when it learns knowledge of one type, that type of knowledge actually helps it learn better type 2 knowledge. Key idea number 3 in Nell is another one that has to do with never-ending learning. I'll tell you that if you browse the knowledge base in Nell, you'll see that it has a lot of countries. Countries is one of the categories. And when we started out Nell, we gave it a dozen training countries. It now has many others, plus some non-countries that it's mistaken about. But the point is, if we wait another year, I don't think there are any more countries for Nell to discover. In a sense, Nell has saturated what it's going to learn about the list of countries that exist. But we want Nell to continue to improve. And so we want to somehow organize the architecture of the system so that as it conquers one learning task, like learning about countries, it doesn't just run out of stuff to learn. So key idea 3 in NEL is to give it the ability to add new categories and new relations that go beyond the list of categories and relations that we manually gave it to get it started. And NEL is now doing that. So let's take a look. First, let's take a look at its ability to add new relations. And in fact, I have to tell you, when we were browsing diabetes back at the beginning, you saw some relations with funny names like, I don't know, inverse of emotion associated with disease or something. All of those funny name relations were ones that NEL made up and that were not part of the initial ontology. So how does it do that? Well, and this work, I should say, is due to Tahir Mohamed, one of our students, and Stefan Hrushka, visiting professor from Brazil at the time. What they did was they said, well, let's have an algorithm that goes through each of the categories in the current ontology, in fact, each pair of categories in the ontology, and looks at what's known about those two categories and look for statistical properties. So let's take an example. Suppose we look at the category C1 is people, C2 is musical instrument. Then NEL might know that Eric Clapton, it might believe Eric Clapton is a person and guitar is an instrument, and it might notice in the text that Eric Clapton and guitar co-occur in the same sentence way too often to be coincidence. And so do George Harrison and sitar and some other pairs. And so that's kind of a signal that something is up. People are out there talking about these things way too often for it to be random chance. So there might be a relation there to explore. So Tahir and Stefan wrote this algorithm that simultaneously clusters the pairs of known instances for each pair of categories in NEL and the text that occurs between them. And what you find, for example, in the first row here is if you start with the category musical instrument and musician, you find pairs like sitar and George Harrison occurring together, and the other is shown here. And you find them occurring in these particular text contexts. Like you find sitar master George Harrison, tenor sax virtuoso Stan Getz, sitar legend George Harrison, and so forth. So these are the text phrases that people are using to talk about that anomalously frequent relation between people and musical instruments. And so NEL uses the centroid of this cluster of text contexts, which happens in this case to be the word master, to suggest a name for the relation. In fact, it ends up naming it music instrument master musician. And here you see in the same table a number of other examples. Right? So now when it looks at disease and the category disease again, it finds disease is due to disease, like pinched nerve due to herniated disc, or cell type that release chemicals, like epithelial cells release surfactant, and so forth. So this is an example of the types of learning that can be done that NEL could never do during the first 6 months when it was running, because it just didn't have enough knowledge about the world to even know who were the musicians, what were the musical instruments. And that was kind of a prerequisite, if you think about it, for learning these, discovering these new relations. And here is a list of some of the other relations that NEL has proposed and that we have allowed it to add. We maintain veto power on NEL's proposed relation additions because sometimes it proposes things you wouldn't want to add. For example, it found that lions occur a lot with, tigers occur a lot with Detroit, rams occur a lot with Los Angeles, and some other animals occur in other cities. And so it proposed the relation animal and city, but actually they were just sports teams in cities. So there's an example of a kind of statistical regularity NEL could find that we didn't want it to go ahead and add that as animal lives in city relation. Okay, so you get the idea. let me just say that we're also, there's a second route toward learning to extend the ontology. We can look at this statistically, as the first algorithm did, but since NEL is a reading system, we could also ask NEL to try to read what are the categories and subcategories out there that people talk about. So Burr Settles, one of our researchers, came up with the idea of just adding another relation for NEL to read, the subset of relation. And so, for example, he trained it to read among animals. He defined the relation, animal is a subset of animals, and gave it a few examples, and then NEL learned to read which animals' subsets existed and who their members were. And by reading, it found that there's a subcategory of animals called pets that includes hamsters, ferrets, etc. And here you see some of the extraction patterns at the end of the slide that it used. So, for example, it finds bears and other medium-sized predators. And that's how it decides that bears are predators. And it finds predators and other medium-sized animals to decide that predators are animals at the same time. And similarly, for chemicals, it discovered that fossil fuels and gases are subcategories of chemicals. Okay, so you get the idea. And I just want to wind up by summarizing. I mentioned there were 4 key ideas in NEL. The first one was that learning idea. How do you get a system to learn from mostly unlabeled data? And remember, key idea 1 was you get that to work by forcing the system not to just learn one function, because that's too hard, but instead force it to learn thousands of functions simultaneously, and they're all coupled so that the system can drive itself not just toward fitting the labeled data, it doesn't have very much of that, but so that it can also drive itself toward becoming internally more consistent in the collections of labels that it assigns to all of the things that it's reading. So that was key idea 1. It's an idea about how to manage the learning. The second idea was really about inference. The idea that we should data mine the collection of beliefs the system is building up, or the system should, in order to learn inference rules and then apply those in order to reason about and infer new beliefs that it has not yet been able to read. And we talked about how that feeds back to better reading. And in fact, we have a very significant effort going on we have even a newer way of doing that kind of inference these days, which my colleagues William Cohen, Ni Lau, Matt Gardner are working on, that provides an even more scalable inference method. The third idea was this idea of extending the ontology automatically so that the system can continue to create new learning tasks that build on the things that it has learned before. And the fourth idea is really one that's been implicit in all that I've said, which is if you want to build a never-ending learning system, then just like people, you need to organize things so that it starts out with the easier learning tasks, like just try to figure out which noun phrases refer to which types of things. And later on, once it partly masters that, then you can give it more challenging things, like automatically try to discover subcategories of animals, or learn empirical regularities that hold between teams and players and sports and positions and so forth. So here you see, in fact, a kind of sequence of learning tasks that NEL has taken on. The red line is there because we haven't gotten below the red line yet, but you can see some of our aspirations from here. So let me end then by thanking you for being attentive. I'm taking that on trust because I can't really see you. But also, again, thanking ACM for making it possible to do this, and urging you to follow NEL on Twitter. NEL now has a couple thousand followers on Twitter. I hope you will join. We have big plans for Twitter in the coming year, and we need many users to help us. You could be able to give some feedback to NEL and hopefully have some conversations with it over the coming year. And also, here's the URL where you can go and track Nell's progress. Download the knowledge base and use it yourself if you like. And with that, I'll end. Thank you.
Thank you, Tom, very much. It's incredible. There's been lots and lots of questions posted, ranging from curiosities to very, very deep technical questions. So I have the very tough job of picking a few. So let me start with one that might be of general interest. There were a lot of questions that went around the topic of there's a lot of misinformation on the web. There's also sarcasm. There's metaphor. There's fiction stories that introduce fictitious countries. Does Nell really decide what pages to read? Does it read the whole web? How does it handle things that we all know are not real? And the related question was, will it learn that tomato is really a fruit, or will it believe, like most of us, that it's a vegetable?
That's great. I like those questions. They're right on target. Right now, if you think about the way Nell learns, or reads, I should say, which is by aggregating evidence that it gets from many different web pages, right? Remember, it decided that diabetes was a physiological condition because it found it in hundreds of different phrase contexts. So you think about that, you realize that Nell is actually, because of that style of, let's call it macro reading, aggregating evidence from hundreds of millions of web pages, it's pretty much a believer implicitly in the idea that the majority is right. So Nell will believe that diabetes is a physiological condition, or any other belief, if the majority of people make that claim. And if there are a few people who claim otherwise, that'll just not be enough to carry the day statistically, since that's how Nell is doing the macro reading. Now, interestingly, that's about to change, I hope, because one of our aspirations for Nell is, now that it has acquired this knowledge by that kind of diverse macro reading, we want it to learn to read individual sentences more like you and I do, in great detail. And then it'll be much more susceptible to running across an outlier sentence where somebody says something crazy or untrue, or at least just in disagreement with somebody else. And so I think there's a great research problem in trying to, for example, label which documents support the belief system that Nell has, which in turn reflects the majority opinion on the web, which documents are contradictory to that belief system, in which ways, and Nell doesn't do any of that yet, but it's a great research area.
Great. There's another set of questions that are really interesting, and they go around the topic of how do you evaluate, or how do you know that Nell is learning useful things. So one question talks about whether you have thought about testing and quantifying Nell's ability to learn in limited worlds or limited domains. So they suggest the medical literature or the Harry Potter books. Someone else asks how to evaluate that you're really improving every day. How do you assess that? Another question is, what date will Nell approach human intelligence? And perhaps more realistic asked, when will Nell be able to play Jeopardy? So how do you assess or evaluate Nell's progress?
Yeah, I like that cluster of questions. Let's see. Let me take them kind of in turn. So what about making Nell an expert in some area, like you mentioned, the medical literature? We're very interested in doing that. In fact, my colleague William Cohen has done, along with one of his students, a quick experiment augmenting Nell's ontology with a medical ontology that it obtained from that community, and then having it train it or read online journal articles. We had limited success with that, a little bit, but it was just a quick experiment. It was enough to make us realize that you want to still retain Nell's broad, diverse ontology and add to it the more detailed medical ontology if you do that. You don't want to throw away what it knows about sports and insects and things like that just because you're reading medical journals, because people talk about everything inside journals. But I think that's a good idea, and it's related to the other question about how do you evaluate Nell anyway. And I think there are broadly speaking, two broad ways of evaluating it. One is correctness, the other is utility. Correctness, one way that we do this is we use Amazon's Mechanical Turk service. We'll take a random sample of Nell's beliefs. If you go to the Nell's website yourself, you'll see a random sample of 10 recently read beliefs, and you can evaluate which ones you think are correct and incorrect. And you can give a thumbs up, thumbs down to give Nell some feedback. But we can do that on a larger scale just to see whether people agree with the beliefs that Nell has. So that's correctness. The other one that I think is really interesting is utility. So, could Nell do something useful, like help you plan a trip or help you register for a conference or something like that? And right now the answer is Nell isn't competent enough to support those kind of tasks. And one reason, the main reason I think, is that it's not a targeted reader. That is, if you think about the infinite loop that Nell is in, every time through that loop, it's just cherry-picking more things on the web that it can now understand because its reading competence has increased a little, but it's not doing it in with some particular use in mind for the knowledge. And so a big push that we have on for the coming year is what we call Nell Knowledge on Demand, where you would be able to give Nell some query and come back the next day, and Nell would have done its best effort to try to do some targeted, directed reading to answer that query. And I think if we can do that, if Nell can learn to do that, then it'll be in a better position to do a good job on the utility measure of progress. For example, then you could say, I want to plan a conference trip to next summer's AAAI conference, and even though Nell might not currently know all the things it needs to know about the town and hotels in the city where that conference is, if it could do targeted reading, it might be able to go out and then do something useful.
That's great. I'm going to ask you the last question, and we don't have a lot of time, but we do have a couple of minutes. So there were a lot of people curious about whether and how you could combine Nell's learning with more training data that could come from databases. For example, giving it a big list of countries, or using things like DBpedia, which has a lot of facts extracted from Wikipedia, just to help Nell bootstrap from all this data. That was a question from Twitter. So how would you handle this?
Yeah, that's a really big opportunity, I think. To do that, of course, you'd have to start by aligning Nell's ontology of particular categories and relations to the ones that you find in DBpedia, and probably extending the ontology to cover ones that are in DBpedia that aren't in Nell yet. We do have some work in that area. In fact, Dari Wijaya, one of our PhD students, and Partha Talukdar, one of our postdocs, have a paper coming out in the CIKM conference this fall in which they tried to automatically align Nell's ontology with Freebase, which is one large open source fact base, and also Yago, which is another large one from an effort in Germany. And so we're looking very carefully at whether we can align these ontologies, and if we can, then we could create a kind of union of these different efforts that are going on around the world to build these large-scale knowledge bases. So we're not there, and it is a non-trivial problem, but I very much am interested in that direction.
That's great. There's many other fantastic questions. Does NEL run on a supercomputer? How does it deal with aging information that becomes obsolete? How does it handle different domains? How does it make relationships across domains? When will it pass the Turing test? How can we visualize what it knows? Can you bootstrap it in different ways and try different instances of NEL? So these are all fantastic questions. So I'm afraid we have run out of time, and I'd like to thank you, Tom, again for a fantastic presentation, and thank our entire audience for taking the time to participate today and for all your many great questions. The webinar was recorded and will be available online in a few days at learningacm.org/webinar. And you can find announcements on upcoming webinars and other ACM activities at learningacm.org and at acm.org. Also, please fill out the survey by clicking on the URL that you see on your screen, where you can suggest future topics or speakers. And thank you, everyone. This concludes the webinar.